Hello, everybody. Welcome back. So please take your seats if you haven't as we continue on with our program for today. Now, everybody, in an era that's marked by geopolitical volatility, supply chain disruptions, as well as shifting consumer demands, agility clearly has become a strategic imperative for manufacturers, which is why, in just a bit, we will be exploring exactly how additive manufacturing empowers decentralized production models to enhance responsiveness and resilience, enabling organizations to adopt glocalized manufacturing strategies. And to tell us more about this, could you please put your hands together to welcome Dr. Terry Wallace, Distinguished Fellow of Advanced Manufacturing, Wallace Associate, powered by ASTM International.
Thank you. So I've been asked to give a few minutes of opening comments for this important session titled Agile and Distributed Manufacturing with AM. You know, we learned a lot. I learned a lot. I think many of us did. In 2020, from the pandemic, we had supply chain disruptions, and it was utter chaos for a period of time. And none of us want to go back there, but we all remember it vividly. Companies with AM capacity stepped in and manufactured nasal swabs, face shields, and ventilators, and it was distributed manufacturing at work in a very big way. You know, as inventories become digital over time, and they will, parts stored on servers instead of on shelves, agile, distributed, and just-in-time manufacturing becomes more practical. And this has come about largely due from additive manufacturing. But it's taking much, much longer than some of us expected. I do believe that AM will reshape supply chain strategies. I think that's going to happen without a doubt. And it's a real privilege for me to introduce this important session and subject with use cases and insights from a terrific lineup of speakers and panelists. So thank you, and we'll turn it back to our hosts.
Thank you very much, Terry. So, of course, with that, we'd like to welcome our next speaker on stage in just a bit. Now, he is responsible for strategy, development, and deployment of additive manufacturing and advanced metal technologies. He is equipped with 18 years of aerospace product development experience and is also a recognized leader in additive manufacturing with over 12 years of AM technology development and AM production transition experience in aerospace. Could you please welcome Mr. Nicholas Moulet, Director of Additive Manufacturing, Boeing, telling us more about reshaping the future of aerospace production with additive manufacturing. A round of applause, please.
All right, good afternoon, everyone. Thank you for opportunity to speak with you today. It's a privilege to be here. So as shared, I'm leading the Boeing Additive Manufacturing, or BAM, as you might have heard it, across Boeing. And we are a technology vertical, really. All things additive. We're a corporate group that developed the technology from beginning to end. So what I wanted to talk about today is where are we today at Boeing with additive? Give you a little bit of a perspective, and where do we need to go in the future to scale the supply chain? So definitely want to touch on distributed manufacturing, how we're leveraging a lot of our digital technologies to support, and really think about what I see as an inflection point with additive. For companies that invested early, really identified the right use cases where additive is going to help you grow and develop products, that is now coming to a head to really turn into how do you scale all your investment, and in my case, aerospace, scale that with quality that we need for our products to be safe, whether it's a commercial airplane, or a satellite or a defense product. A lot of really strict requirements we need to meet just to meet that safety. So to give you a little bit perspective about Boeing Additive, worldwide operation, have about 20 sites across the globe, heavy presence in US, and you can see within Europe and across our different partner sites across Boeing, doing a lot of additive research and looking at technology development, partnering with companies around the world to develop key aspects of the technology, prototyping. We have just printers across the whole world. When we're taking a step back and kind of looking at where is additive today at Boeing, it's been over 20 years. It's not new to us. We have over 140,000 parts flying on Boeing platforms today. So if you're looking at the whole portfolio, pretty large number. So on any given Boeing product, whether it's a commercial plane, whether it's a defense platform, which could be a military aircraft, helicopters, or satellites or drones, we have additive content that is really helping our products perform. And it's really building on decades. If you hear other additive journeys, starting way back 20 years ago, looking at polymer, looking at lower criticality parts, looking at where additive can support prototyping, tooling, shop aids, a lot of different areas where it's adding value to the program. And then as you mature in this technology, you have the workforce expertise, you're increasing in criticality. The parts are getting more complicated, they're getting more mission critical, more safety critical, and with that is a tendency to shift towards metallic solutions. So if you're looking at the portfolio, metal additive has been growing significantly over the years and being baselined in our products, where it's AM by design from day one. And that's an important piece too, just to kind of leverage where additive is going in the future and where we need to go to scale it up. In terms of just highlighting what aspects of additive we work, it's not just printing. If you're looking at AM technologies across the board, a lot of focus on laser powder bed fusion, metallics, very, very common technology in production today. But we're heavily investing in developing DED wire, DED powder, cold spray, friction stir additive, really the wide portfolio. And along with polymer, looking at FFF, looking at SLS, and those technologies have been proven for some time at the company. But when we're looking at additive, and something I really want to emphasize on scale, and as you're looking at your production system and you're looking at how to create a distributed model, it's much, much more than just a printer, which I think many of us probably recognize, but to emphasize it, additive, to deliver an additive part, I would say is probably 20% of the time is printing it. You have a good printer, you have a good process, you have it stable. If you're aerospace and have high stringent requirements, a lot of time and care to do that well. 80% of your time is after print is done. And not highlighted up here, there's about 13 steps for a powder bed fusion part, which are pretty common. And in order to scale additive, you have to be proficient and integrated here as well. So something to really highlight. Practical things, you need a heat treatment furnace, you need a bandsaw or an EDM to cut off a build plate, you need machining and inspection equipment. So if you're trying to scale additive, it's the whole picture. And without that whole picture, you can do local printing, but a final assembly that can go on a platform, that's just really a key distinction. So when we're looking at scale, I recently, I lead all of Boeing Additive at the company. So polymer metal production development across all the business units. One of the first responsibilities I had was developing the digital transformation capability, which I'll go into a little bit more today. So how do you take additive, take all the physical processes you need, take all the regulatory environments you need, and leverage other technologies to be able to scale efficiently? Modeling, simulation, smart factory, data analytics. It's a big portfolio, and I want to highlight a bit of that today, because that really comes into key enablers if you're going to scale your supply chain in a distributed fashion. Because I think these are basic tenets. Without it, you're going to have pockets of excellence, but if you're not connecting them together, it's going to be tough to scale because of the nature of the technology and the information needed to make good decisions, I think, within additive. So highlighting just where additive is adding the most value, or where are we really prioritizing its use at the company. Big focus is on clean sheet, new product development. Biggest value add, biggest area of focus. This is an area where in the bottom middle image is a CubeSat, small satellite. Whole product lines that are 3D printed that enable performance and a lot of other attributes in terms of schedule enablers, doing things at fraction of the time to meet our customers' needs. Additive is the reason it's successful, and that's where we can see additive drive adoption because the value is clear. But across the board, we want to see where additive can add value. It can be consolidation, which we heard Terry speak about earlier, consolidating parts, cost avoidance. You're not mechanically assembling or welding parts together if you have the opportunity to redesign. And you're looking at, really in a big focus area as well is sustainable solutions. So there's sustainability, which is important in terms of how additive can help, but sustainable to our platforms, meaning spares and repairs, and you have pathways to help get parts to critical platforms, which might be undergoing obsolescence issues, decades-old platform that it's hard to find a part. You might have aircraft on the ground where your key business case is getting it back up relative to unit cost, and that's where additive can solve this, but it has to be in that whole context, not just a printer and a file, it's the entire beginning to end process. And so that's what we have to cover. So giving a sense of just where you have new platforms, new products, this is an example of the small satellite business. It's been growing significantly. Here on the screen, you're looking at just fully 3D printed structure. So AM by design. Enabled a whole product line, as I mentioned. And you can see some of the metrics up there that continue to improve, especially when development time expectations are shrinking. The other aspect, which isn't highlighted on the screen, and perhaps you saw in a press release a couple weeks ago, now we're adding to this, and now we're printing solar array substrates. So now this is the satellite structure, the bus, and the actual solar arrays themselves now are the longest lead time component. And now we're going to be printing those as well. So now you're enabling all the things that additive helps you solve as just an example of the business. So this is an example of an anchor program where without additive, it's not possible. And building on this success across different areas of the business, we want to continue to use the technology, and it's going to vary by business unit. This is a very specific set of needs enabled a product line. On the defense side, you have sustainability issues you need to solve and resolve from spares and repairs. And similarly on commercial, we have a broad portfolio where we're trying to adopt additive. So an example now on, call it a spare and repair side. This is an exciting project. It's been ongoing. It's a F-18 landing gear bell crank. When you hear landing gear, the criticality is increased. It's an important application. We partnered with NavAir from day one just to go through our process beginning to end. Understand how we develop a process, how we qualify a powder, how we qualify a machine, how we generate data to say it's aerospace ready and it's meeting requirements. This particular material was, it's really replacing a long lead forging, and it's using a high strength aluminum material that we developed that not only just fits the requirements of this part, but also has inherent corrosion resistance improvement. So it has a 50x improvement on corrosion. So it's really, from a performance standpoint, we're hitting all the technical airworthiness requirements. So last year we had a fit check at a air station just to prove out the concept, and continuing to drive forward these types of applications where it's no longer a technical issue. We can meet requirements, we have stable processes. But how we drive value into these programs by building confidence to the end users, working with our regulators on detailed reviews on maturity so that we can really solve some of these needs. So I kind of highlighted this a bit and from the sheer volume over the years, but as we're starting to scale additive now, we're going from tens to hundreds to thousands a year. What we really need to do is take a very complex interdependent process. Many variables for powder bed, easily can be over 100 variables that you have to lock down and control, especially in aerospace, aerospace mindset. Without those understood and locked in, you're not demonstrating a repeatable, reliable process, which is foundation for any regulator. You can demonstrate repeatability in your process. So the key to scaling and developing a supply chain is a digital thread technology and system behind it, as well as a model and a supply chain to help us scale in the ways that we think we need to be successful. So one aspect of that is developing a digital thread. That's where we're looking at a number of activities. One, beginning to end, all of the engineering data, all the manufacturing data, all the inspection data that you might need is developing a back-end infrastructure to store that. So what that has meant is we have developed an entire data architecture where we've automated our machines, connected them to a central database, integrated them with engineering and manufacturing systems. So you have data that has context. So you have a giant structured data set, and that can scale. As you buy more machines, you add a node to the network. As you work with a new supplier, you add a node to the network. And you're able to now have data with context so the engineers aren't having to figure that out on themselves. You know, go to a machine, download data. Those are the things of the past. What you need to have is automatic validated data that's structured. That's an enabler. If you have that, then you can build complex analytics on top in a more easy fashion. So as an example of this, this is one of another satellite application. This is a wideband global SATCOM, WGS. This is an example where over 1,700 additive aluminum parts were integrated in a passive microwave device. So you can see the very complex assembly of the parts and how they're stacked up. Bottom line business case in terms of savings and schedule reduction, it's the best technical solution here is using additive. But when you're looking at how does digital thread enable it, we've developed simulation tools to increase yield. So you're not having to do manufacturing iterations, predict deformation, adjust the design. Machine automation, we can automate sensor data from each of the machines. It can be environmental, it can be more complex in situ cameras and things to do analytics. Was there an issue with my build or not for decision making? Integrating machine data with inspection data and integrating it all together in one reference frame. My machine did one change here. Did it show up on inspection data? Structured data lets you do all this. So the back end is helping us scale. So now if you have kind of you've proven out the technology, you have a digital thread as enabler, how do you scale it? One of those key enablers is what we are developing is a distributed manufacturing model and a secure distributed manufacturing model. How it's done today, you may have a geometry, a supplier may iterate or update and determine how best to print it. There might be local knowledge to drive that decision. But if you look at the upper left image, that's variability in your system, and it can drive local change. And if you're scaling at volume, you want to limit where change can occur. And so we look at build file development and the design for additive as upfront engineering. You want to lock down your build file, your orientation, your configuration, all the developed parameters, and just lock it down, and then encrypt it send it to a qualified printer. Now that printer can be anywhere around the world where it's needed. And you're limiting opportunity for variability by doing so. And so by doing this model, we have the ability to take all of the comprehensive variables that go into qualifying and certifying a part. And we're establishing it, we're locking it down, we're putting it into a fully configurable format, encrypt it, and now you're sending that across. And it's okay, my map got off a little bit off on the chart. You can send it anywhere across the world where it's needed. All right, so you physically have a site with all the equipment. You have the ability to send it encrypted and get data back, and that's a key functionality we have, where now the data is connecting back to your digital thread. So you have a fleet of machines across the world. They're all fully connected, and you're able to integrate that in one central database, which is really a enabling piece for us to scale at quality, where you have these complex processes. So when you're looking at that kind of complexity here, and you're looking at what does that mean in the future, where we are today, and just maybe to highlight this as I wrap up my thoughts for the next session, is right now we know how to qualify parts today. We have certain standards across the industry. We have very proven methods, whether it's with the DoD or the FAA, where data needs to be presented and them accepting it. The digital thread helps us scale because the data is available and accessible. Something I have to juggle is we have to meet regulations today with data, but we also want to develop new methods of the future so we can be more efficient as we scale. So part of the enabler for the digital thread is being able to develop more complex ways of qualifying parts, where there's a lot of excellent research in the community here and also at large to advance laser controls in your machine, being able to do feedback loops to be able to control a machine using novel algorithms. We're using machine learning and AI to control the systems. All very important work, but it has to be in the construct of how are you going to certify that part in an aerospace environment. So the digital thread in our distributed model will help us scale with proven methods today for qualification. But keep in mind, there's future ways that we need to keep working together to scale further and more efficiently. And we have to keep working both solutions. Yeah, we know it works today, but we have to keep our eye on the future and how to do it. So, I think with that, I just wanted to, say, thank you all for the opportunity. And really, I think what we're at as an industry is an inflection point, as I said, scaling up in production, and how do we leverage modern digital tools, secure transmission, digital technologies to help scale additive to the next level where we're trying to go. So thank you very much.
Thank you very much, Nicholas. Now, we'd like to welcome our next speaker coming up in just a bit. He is driving a mission to democratize access to world-class orthopedic solutions by leveraging on innovations in advanced manufacturing and precision engineering. And with a strong belief that cost should never be a barrier to quality care, he focused on building a scalable, tech-enabled infrastructure that reduces production costs while ensuring rigorous clinical and regulatory standards. Please put your hands together to welcome Mr. Sri Shetty, Chief Executive Officer, OIC International, to talk about navigating through evolving demands of a highly regulated industry. Let's welcome him.
Hello. Thank you for giving me the opportunity to talk here. I'm Sri Shetty. I'm the CEO of OIC International. And today the topic I'm going to target is navigating through the evolving demands in specifically the regulated markets. That's the medical markets. So today, if we look, OIC is targeting the developing countries in Southeast Asia and India. The three main challenges that exist in the market today, specifically in medical devices, is as follows. The first one is that the existing devices that are really cheap have poor quality, really bad patient outcomes. The second challenge is that the multinational products that come from the West that have high performance are extremely expensive. And the third thing is that over the last 20 years, all medical devices globally have been designed for the Caucasian body type. That's because that was predominantly the market. And as you go from the West to the East, a lot of these devices do not fit. At OIC, our mission is to basically use advanced technologies like 3D printing and AI to create devices that are life-changing, both in terms of high performance and low cost. We use AI, a combination of AI, additive manufacturing, and semiconductor technology to create the next generation of orthopedic devices that would not have been possible even maybe 10 years ago. So the business model is as follows. There are four parts of the business model. We target predominantly developing countries with large populations, Indonesia, India, etc. The second is that we use advanced technologies. We go away from traditional manufacturing and we use advanced technologies like 3D printing, like semi-tech, combined with AI to create low-cost, better-fitting devices. The third is that we partner with a lot of local companies, local governments, local joint ventures. And the last thing is that we hire teams in the country itself. We use Asians to target Asia, Indians to target India, and that is the basis of the business model. So if you look along those lines, Today, our presence is, we are heavily, we have high presence in the US. We have 200 plus FDA cleared devices in the US. We target 70 plus hospitals in the US. We've been in 70,000 patients in the US, but our target market is not the US. Our target market is Southeast Asia, predominantly with the goal taking these high-end US devices into Indonesia, followed by India. Second is that unlike other orthopedic companies, almost a big part of our portfolio is based on digital factories that have a base on AI, semiconductor technology, and metal 3D printing. We also partner heavily in the region. So for example, in Singapore, we are partnered with NAMIC, we are partnered with EDB, we are partnered with all 3 health clusters in Singapore. As we go to Indonesia, we have partnered with Dexamedica and the Indonesian government. Dexamedica is the largest pharma company in Indonesia. And as we go to India, we've partnered with the Indian government and AMTZ, which is a big part of the government sector in India. So as we go through the region, we do not go through individual hospitals. We partner with large partners that have 100, 200 hospitals so that our high-end products can have higher reach. Our management team is predominantly local. So we hire a lot, as we go into different countries, we hire teams that are locally based, of local ethnicities, to help grow the business in the region. A little bit, though we started in the US, as we grow through the developing countries, Singapore is becoming a critical piece of our strategy. We are making our operational base in Singapore. We are just about to open a large 3D printing training and development center in Singapore. Our supply chain base is coming into Singapore. We are also hiring an extensive team in Singapore, predominantly with the goal of making the Singapore as the base, the technical base, and the operational base to grow our businesses into countries like Indonesia and India. We have very key partners in multiple regions across the globe, and Singapore is going to be very critical in terms of that strategy growing through it. The orthopedic industry today has a lot of challenges. There are challenges between traditional manufacturing and emerging manufacturing technologies. There are challenges that the supply chain is very fractured. An orthopedic device is very expensive, takes a lot of time, a lot of shipping, a lot of steps to build the devices. And then there are all the regulatory challenges, which actually make it extremely complicated, and you need many, many companies to build an orthopedic device. The impact of additive manufacturing is that, like my previous speaker at Boeing said, you can take things that are done by 10 different vendors with different steps and integrate it on one 3D printing step that lets you replace large casting houses, large post-processing houses in Asia with a digital factory that has a much smaller footprint, and that helps you reduce costs exponentially. So, as many of you guys know, the main advantage of additive manufacturing is threefold. One is the localization aspect. It is almost impossible for many countries in the world, like Indonesia and India, to put large casting houses in there. They just don't have the space to do it. It's easier for you to put a digital factory in country. The second is cost. Today, a lot of cost in building parts does not exist in the manufacturing itself. A lot of cost in building parts is actually in the shipping, in the inventory, in the tariffs. So if you can have a factory close to the source that is using the products, you can exponentially bring down the price of, and the only way to do that is with digital manufacturing using 3D printing. The third thing is customization. You can take devices that are historically designed for different anatomies and convert it to have better fit in different regional body types. Today, it is a well-known fact that in the West, surgical procedures have really good outcomes, but when you take those devices and put them in patients in Indonesia and India, the revision surgeries, the infections, the fit issues are huge. And using 3D printing to make better fitting devices at lower price is the only way to tackle this huge problem. So if you look at the supply chain for a medical device, from an idea all the way to a product that goes in the human body, there are maybe 20, 25 steps. And this is done by many, many vendors in the chain. At OIC, we integrate all these steps on a common platform, and by partnering with local healthcare partners, we bring it into countries. And by having this ecosystem local in Indonesia, in Singapore, in India, we are able to create the next generation of medical devices that historically have not been possible in the past. Because historically, medical devices were created in the West and sold in the East. By bringing this innovation, manufacturing, development, and regulatory platform in the region, we are able to have local products created for local population, which is very critical as the population starts aging and growing in the developing countries. AI plays a pretty significant role in this as well. Historically, designing products has been a pretty complex and a long process. It could take you anywhere from 1 month to 6 months to design a product. A lot of the AI tools help you cut the time down and helps you get designs that are much more robust than anything that you could make in the past. The second thing is modeling and simulation. A lot of orthopedic devices, a lot of aerospace devices are made in complex materials, using complex technologies like 3D printing. Modeling in the past has been an extremely time-consuming, difficult process. Here is where AI plays a key role right now. Things that would take you months in the past, the AI models today can actually help you create these products a lot quicker and with much higher strength and performance. And the last thing is manufacturing control. Historically, the methods used in traditional manufacturing have got to do with SPC charts, creating, looking at data, and trying to figure out how to build these parts correctly. AI helps you do this a lot more effectively, which in turn leads to higher yields and lower price. So you can get better design products, better fitting products, stronger products with much higher yields and lower cost by combining digital technologies with AI. So in my last slide, I'll say that it is very, very critical that orthopedics goes a certain way because it's one of the basic needs of the developing countries. And we need to think about these models differently than we have in the last 50 years. So basically, I say data-driven manufacturing technologies, putting manufacturing capacity in country for local demand, personalized implants that historically were not available for cancer patients, for spine patients, having healthcare equity through innovation, and finally, Singapore will play a key role because a lot of the countries that we are targeting, where there are large geographies, 300 million people in Indonesia, 1.2 billion people in India, they are all around Singapore. Using Singapore as a hub to do technology development, to help innovate into these developing countries is very critical. And this is a journey that OIC was created on. This is a journey that we've been on in the last 7 years, and it is just the beginning. I think it's a critical need, and hopefully between technology, partnerships, and people, we get there and try and make a small change in this big problem. Thank you.
Thank you so much to Sri. So with that, everybody, we'd like to welcome our next speaker who's going to take the stage in just a bit. Now, of course, later on, we will be having a panel discussion. So if you'd like to submit any questions, feel free to scan the QR codes located at your table. Now, coming back here on stage, we have our next individual who is so very passionate about building scalable sales system, developing emerging leaders, and helping companies accelerate their commercial success. Equipped with over 30 years of experience in revenue growth, team building, as well as strategic operations, he has built and led high-performing sales organizations, driven double and even triple-digit growth. Please put your hands together to welcome Mr. Jim Golden, Vice President of Sales and Marketing, Fabric 8 Labs, telling us more about mass production of next-generation 3D printed electronics. Let's welcome him.
Good afternoon. I'd like to say thank you for inviting me to present this afternoon. And I'm Jim Golden. I'm the Vice President of Sales and Marketing at Fabricate Labs. I'm going to talk to you a little bit about our technology and how it's used in the printing or the fabrication of next generation electronics. So we're based in San Diego, California. We've been around since about 2015, and we have about 120 employees, so still relatively small but growing very quickly. We've developed a revolutionary technology that is unique. It's proprietary technology called electrochemical additive manufacturing, or ECAM for short. And what it is, it gives you the ability to create high-resolution 3D metal printed components. And you can see we've got a picture on the upper right-hand side. We've got two different facilities in San Diego, and we also have a picture of some of the printers in our facility. We don't sell printers, we sell parts. We're a manufacturer of parts. And we're scaling for high volume production. That is quantities in the thousands per year to many thousands per month. So high volume production. We're going to grow our facility from the two buildings in San Diego. We're going to be adding another facility in North America, and then after that in Asia and Europe as our customer requirements dictate. So we have three primary markets that we serve. One is thermal management, and there's a picture there of a cold plate used for direct liquid cooling in an AI or high performance computing application. This is in a data center. We also have wireless components. We make wireless and RF components. We have quite a few customers in the aerospace and defense world. And then we also manufacture power electronics components. And in this case, you can see we've got the ability to print some of the structures on one side of a substrate, and on the other side, we can print thermal management structures as well. So what is ECAM? ECAM is based on two very mature technologies. One is TFT displays, and the other is electroplating. Okay? So in the first case, our print heads are 120 millimeters by 120 millimeters, and we have pixels on those print heads that are 33.3 microns center to center. So we have millions of pixels on that print head. Across that print head will flow a plating solution, in this case a copper sulfate. And we can selectively energize the pixels that will cause the copper to deposit. So we're building components essentially at an atomic level. So what can you do with ECAM? Here are some examples of geometries that we can print. And these are taken from our direct liquid cold plate products. And so you can see we can print pin fins, we can print flow directors, we can print covered channels, we can print features for finned cooling structures that are 100 micron size, 100 micron spacing down to 80 micron feature size. And we can also then print finlets, very small geometries, right? So a great deal of design freedom. And this is important because what I'm going to get to here is now, so why would you use ECAM? And well, so this is a picture of kind of a typical supply chain that we're participating in. This is, again, for a cold plate for an AI application. This is based on, I think that's an AMD component there. And so you can see we've got, on the left-hand side, we have our cold plate insert. And on the right-hand side, that's the overall assembly for a cold plate. On the right-hand side, this is what is shipped to the data center or shipped to the server manufacturer who then puts it on a server and ships that off to the data center. We don't want to be in that business of doing the assembly, the brazing, the testing. We want to focus on ECAM, and that's the left-hand side of that slide. That's the insert that we'll make, okay? And so in order to scale our production with our customers and support our customers, we form manufacturing partnerships with other companies, contract manufacturers, OEMs, and the like. These companies are typically already part of our customers' supply chains. So they already know, they do all the machining, the assembly, the brazing, testing, all of that. So all we have to do is we focus on the delivery of the component. Now, right now, we're shipping everything from San Diego to these companies, and they'll do the assembly and ship that out to our customers. But from a supply chain perspective, we can eventually then either co-locate to somewhere nearby these facilities or even put a factory in a factory to help support our customers. But either way, by doing this way, we can significantly reduce the amount of supply chain risk for our customers. The overall assembly is already qualified. We're not changing much except for one component. So that makes it much easier to introduce a technology like eCam. So why would you introduce a technology like eCam in the first place? First of all, on the left-hand side, this is a picture of a copper skived insert. And copper skiving in the data center world, it's the dominant method of cooling AI and high-performance chips. You kind of see there, it's uniform fins going across the substrate. Contrast that to the picture on the right. That is our design, which is a variable fin density, and that has several key advantages. All right, so in the first case, the copper skived, you've got a relatively straightforward amount of cooling. It's very consistent across the surface of that cold plate. Unfortunately, most dies in the AI world, most chips have a very complex power map. And so you have those red circles, you'll see there, those are hotspots. And so you've got a very consistent cooling, but you've got hotspots, and that's problematic for these devices. On the right-hand side, if you look at our component, the variable fin density, we can use generative design and to create a cold plate insert that actually reduces the statistical variance across the device. In fact, we can improve statistical variance of temperature by almost 250%, and we can improve the overall thermal performance by almost 40%. So it's a significant benefit to our customers. That's why you'd introduce a tech like eCam. This is an example from our power electronics products, and in this case, standard process flow is up on top. All right, so you've got a substrate, you're going to put down components, you're going to put down dies, wire bond them, you've got to go through a lead frame attach, you've got also some terminals you've got to attach, then you can do some transfer molding, and then you're going to do some trim and packaging. Contrast that with our process. So you start with a die attach on a substrate that has already got many of the components already printed on it. So you're already simplifying the process. You do wire bonding and go straight to transfer molding. So you've got a component that uses fewer process steps, fewer components, and actually takes up less room, which is a benefit to board designers. So again, we're simplifying the supply chain here. These are our applications here. We've got a couple of different examples. On the left-hand side, the upper left, that's a Vivaldi array antenna. The upper right is a phase array antenna. We've got a spiral antenna. We've even got an automotive radar. So typically, when you manufacture these components, you have to take each one of those elements of the device, and you've got to discretely manufacture them and then solder them to a circuit board. With eCam, we can actually print directly to the circuit board. So we eliminate that entire process altogether. Okay, so we're again simplifying that supply chain, but there's an added benefit too. Because we can print so precisely, we're actually able to improve the performance dramatically for these components. In the case of the phased array antenna on the upper right-hand side, the distance, and I don't have a pointer here, but the distance between the elements on the far left and the far right are very precisely controlled. In fact, our tolerance in the XY is plus or minus 17 microns. And so because we were able to print them all at the same time, we're getting significantly improved performance. And as an added benefit, that component represents a 10x price reduction for our customers. So again, simplifying the supply chain, simplifying the process flow. So we've gone through kind of what eCam is, what it can do, the benefits of it, and how we kind of integrate with the supply chain. But let's talk about the supply chain of the electrochemical additive manufacturing process versus a traditional laser powder bed fusion process. So we will start with copper ore, right? We both start in the same place. But if you look at the top row, ore has to be converted to refined copper, has to be then converted to billet, then to powder, then you print it, you have to depowder it, you have to sinter it, and do any post-processing, and then ship it. Compare that to the ECAM-based process. We start with the same copper ore. In fact, we make our solution, our plating solution, with scrap copper, copper oxide. And that goes right into the printer, and out of the printer comes a finished component. No post-processing, no depowdering, no sintering, and we're done. In fact, we had an analysis run several years ago that declared that our components were about 95%, at a 95% lower carbon footprint than laser powder bed fusion, and about 91% lower footprint than binder jet. And it's due mostly because of the lack of sintering, a lack of atomization for the powders as well. So again, another supply chain improvement overall. So in summary, what is the outlook for ECAM? We've developed this process. It minimizes the supply chain risk, making it easier to introduce a new technology by utilizing or leveraging the existing supply chain for our customers. It improves performance for the components that we manufacture. It reduces the component count and process steps, and also reduces the carbon footprint. And if any of you would like to see some sample parts, I do have them. When we get to a tea break, just look me up, and I'm happy to show them to you. Otherwise, thank you so very much.
Thank you, Jim. Alrighty. Now, the next speaker, he spearheads initiatives in advanced manufacturing with a particular passion for additive manufacturing. And as a key advocate for additive manufacturing, he actively bridges the gap between developing as well as mature industrial practices, accelerating adoption of 3D printing technologies across APAC. Could you please join me in welcoming our next speaker? He is Mr. Benjamin Moy, Vice President of New Ventures, ST Engineering. A round of applause, please.
Can you guys hear me? Yeah. So thanks for having me again. I would like to congratulate NAMIC on their 10-year anniversary. I think it's been a long AM journey that Singapore has been on in the last 10 years. And similar to what Boeing mentioned earlier on, Nicholas, I think we see an inflection point. And today we see that AM is not just a R&D, low TRL solution. It is the solution of today. And I would like to say Singapore is ready to take on the challenge for more advanced manufacturing using AM. A little bit on where ST has been on this journey for the last 8 years. I want to set some context. We are an engineering company, through and through. We specialize in industrial manufacturing, and AM is part of the toolkit that we have today. We want to harness the technology. We want to innovate and create a more secure and sustainable world for the people around the region and globally as well. Today, we don't just play in Singapore. A lot of people see us as just purely a defense company. Yeah, actually, we're not. We are doing a lot of manufacturing in mission-critical areas. Aerospace, commercial aerospace, where we do a lot of MRO, and we're the biggest independent MRO across the world today, supporting all the airlines around the world. We have invested in digital cities, yes, creating digital solutions in urban solutions, smart cities. And as you know, we also play a lot in the military and defense. You can see the split in our revenue, 49% in Asia. And we see the demand coming from Asia, actually, in terms of advanced manufacturing. And we want to be spread across the world. Today, we have a healthy workforce of over 19,000 people across the world. So wherever you are in the world, we should have a footprint down supporting you. Yeah. The core engineering expertise is in Singapore, although we have sites in the US and in Europe supporting other customers there, looking at aerospace MRO, looking at defense, looking at smart cities. How did we come about adopting additive manufacturing? Our life really started when we wanted to innovate. What is the next step of cost out? What is the next step of innovation? Our journey started very early on, maybe 10, 15 years ago. We continued to develop the capabilities in design. Leveraging off the IHL, the Institute of Higher Learning, we are able to develop more simulations and enhance our manufacturing capabilities. So we are very strong in manufacturing, traditional, conventional manufacturing, casting, forging, CNC. We build tanks, we build vessels on a very, very large scale. So we know what we're doing in terms of industrial manufacturing. COVID hit us, and that caused a lot of supply chain issues. And that was the government's drive to say, how can we do it in-house? How can we be self-reliant? And Singapore being as small as it is today, we are only self-sufficient and self-dependent on ourselves. And that sort of gave another push to the industry. And that really came out to the last milestone which we have achieved in the last couple of years, which is to really improve performance and sustainability. We're not talking about costing out. Yeah, we're talking about increased performance. We are not talking about replacing obsolescence. We are improving obsolescence part. And that's part of the innovation that the ST Engineering is working towards too. Innovation is the heart of ST Engineering. Today, we have over 100 design engineers in-house, of which we have already trained about 40 of them to be AM ready, additive manufacturing ready. We continue to work with our partners to develop more capabilities. We are looking at startups in more matured AM regions in Europe as well as the US to bring these capabilities to Singapore. Yeah. We started off from making small step improvements in design. We are developing new materials today, lighter weight for aircrafts, for MROs, for our military vehicles as well, for heli lifting. We are embarking on Gen AI solutions for design today. We are also using digital twin. And digital twin helps us short-circuit the process of testing. And they were leveraging all our conventional manufacturing experience. So one case for point is, a lot of the parts of obsolescent parts that come to us today are traditionally manufactured. We have engineers who have done it before, and they understand why certain rivets are in certain places. Certain designs are made to adhere to certain machines for CNC, for example, which immediately the AM design eradicates out. So we know what changes can be made and what improvements should be made without affecting the functional use of the actual part and component. We talk a lot about cost, and in my mind, cost is not the driver, it is the value, it is the true life cost. We're not competing on pennies and dollars, we're talking about the millions of dollars true life costs. We are hoping to enable the supply chain, the service engineers, the operation engineers who replace parts out in the field to have a better performing obsolescence part. We are working with a couple of oil and gas customers today to not only redesign and provide them with an obsolescence replacement, but we're also giving back the extra 10-20% performance improvement. Yeah. And I think there was a chat on the previous session where we talked about who owns the IP, who owns the liability, who owns the certification. Yeah, that's quite a critical part. A lot of us try to work with the OEMs to say, okay, let's help you develop on and help you address your obsolescence issues. Yeah. Many times, a lot of customers say, I just need it to work. And it's a partnership between us and the customer and the end user who feels the pain to develop the solution, and the customer is willing to take the liability. The certification and the qualification of these, I would say, old technology isn't difficult. Yeah, and I don't understand why we take a lot of time to try and validate something that has been already proven on standard functional parts. So I think that's the concept that we need to overcome, that additive manufacturing is not a new technology. It is an enabler, it's a tool that provides the same, or if not better performance in terms of manufacturing. And finally, we also enhance our capability to understanding what design for AM is. Yeah, the criticality of design for additive manufacturing is important because of the portability issue. Yeah, we can either make printers, 3D printers portable, or we make the design of the component robust. And having gone down this path, making the design robust is critical. Yeah. Originally, I was from Siemens Energy, and we made the decision maybe 10 years ago now to convert 25% of our bill of material or gas turbines, and each gas turbine is about 5,000 components, bill of material. And the hard stop from management to say we are going down this path helped save the company almost $3 billion, 3 billion euros every year in part manufacturing. And these OEMs don't tell you that they are replacing with additive manufacturing parts. They just replace it because they own the IP, they own the responsibility for that risk. So a lot of the gas turbines out in the world generating energy today have additive manufacturing parts inside. Yeah, they don't need additional qualification because we know and know how to ring fence the risk. Today, I would say AM technology agnostic. We're not limited to laser powder bed. We're not limited to DD, we're not limited to WAM, we're not even limited to FDM. Yeah, we're happy to explore all technologies because we are a manufacturing house. And we want to use all the tool sets and toolkits within our capability to deliver the best performing component for our customers. From a top-down vision, our management has started off with, okay, how do we protect our design? How can we create designs that cannot be replicated or fabricated? And using 3D design helps us secure and cover our IP. It's easy to reverse engineer old obsolescence parts because it's traditionally manufactured, and we understand that. But once you have lattice structures and grooves and internal structures that you cannot see, this protects our IP. Yeah. So that was the path that we initially set out to do. This morning, we had an MOU signing with the Singapore Armed Forces. Part of the MOU is also targeted at reducing our bill of material. How can we reduce the amount of weight our soldiers carry out to the field? How can we reduce the amount of manpack or equipment that we carry out to the field? By bringing less spares, by combining some of these spares and reducing the number of supplies. We have also gone a step further, which I'll explain later on, further down the slides, on how we are addressing mobility in supply chain out in the field. We have a very deep understanding of all the technologies within our portfolio, and we continue to grow. As new technologies like eCam has come out, we will explore new technologies. And today, we are looking at large format printing, yeah, for vessels, for vehicles, for aerospace, and for land equipment, land vehicles as well. We continue to invest in our people. We continue to grow the capability in-house to address all the different technologies that come out within the industry. We are also developing processes to ensure that certification and process are within certification scope. We deal with MRO in aerospace. We deal with military. These are critical assets that require very stringent regimes. So we are NetCap certified. We have ISOs, AS 9001 as well. So rest assured that the processes in place are of the highest standards that meet industry requirements. The last portion is where we're embarking on today. We are developing mobile fleets to address some of the customer needs. In the previous discussion or panel, we talked about, is a mobile unit like Speed 3D that's deployed in the military, is it efficient? Is it effective? And today, there are a lot of customers coming to us and say they want this mobile unit. The difference is we are working closely with the customers to identify what's inside this vending machine. Yeah. Customers in oil and gas give us parts that we digitalize, we optimize, we qualify. These parts are put on our vending machine, so they only dispense products that are customized to the user. And it's quite critical for operations like oil and gas. They have service overhaul every 6 months at different sites. You can move this mobile unit to the different sites to service all these different plants. And that's the model that we're using today, and we're addressing in the next couple of years with our customers. Today, we are already supplying a mobile unit to the military to support their outfield exercises as a prototype. We hope to do more in order to support our military out in the field. The capabilities we have in-house today is not limited to powder bed. We have a lot of FDMs, we have a lot of polymer machines, and it's all within certified processes. As I mentioned, within the aerospace, we have very stringent requirements for CAS and EASA as well, and we have some of the qualifications to produce some of the parts that go on the Boeing airplane and the lights. And we're happy to say that Singapore is ready. Yes, it was developed in the HQ in the US and Europe, But Singapore is ready in terms of capability to reprint these parts of high quality. Yeah. The aim for Singapore, in my mind, to be an advanced manufacturing hub in the light of our semicon industry is not to develop low-cost solutions. We want to provide high-end advanced solutions that only Singapore can provide, that will give us that niche that will compete against the low-cost China and the low-cost India. Yeah. So when you come to us, we want to develop AM solutions and complex components that give you extra performance and not fight with the low-end cheap replacements, essentially. Yeah. So we want to offer the extra value add in terms of design optimization. We want to provide integrated 300 parts into 4 parts module for you, and not replace the nuts and bolts and screws and impellers that you might require. Today, we are working alongside NAMIC and a lot of the A-star contingents, both in material design as well as component design, harnessing their strength in development, bring up the low TRL components up to a high TRL. And we are partnering with partners who are doing the digital platform today. We are not the masters of everything, so we bring in people who are able to fill our gaps. Today, we have partners within the evaluation phase where they go out to customers and say, let me analyze your portfolio, let me tell you what's commercially viable. And it may be, when they're creating the digital inventory, it could be an AM solution, a 3D printing solution. It could be a traditional manufacturing solution. We are bundling it in that package with our partners, and then creating the digitalization platform, where it's secured and restricted to only the customer requirement. Because we are in military, so we understand how cybersecurity is critical to ensure that customer data is not spread. We continue to optimize using Gen AI. We would love to design from scratch, because that doesn't give us any boundaries in terms of design. Yeah, trying to replace an old part using the old traditional method requires following stringent requirements from the past. If we redesign from scratch, we have a new set of requirements that is more addressable to AM. So we try not to reinvent the old wheel. We try to invent a new wheel completely and enhance the design. Today, we are providing contract manufacturing externally. We want to share the good capabilities that we have built in-house to help enable adoption within the industry, within the ASEAN region and beyond. We are preparing to launch a lease fleet model, containerized AM module, with dedicated digital inventories to the customer for deployment. And that's sort of the direction we're heading to today. We hope to launch this next year, maybe tail end of next year, whilst we trial some of the capabilities we are with our military. That's all I had to share. I think we are on the cusp of a new turning point for AM. Yeah, and Singapore, I would say, is ready with the ecosystem in place to really push and adopt AM and provide services to global customers who have parts that have been digitalized and qualified. We want to have our AM vending machine at all the shipyards and all the MROs and all the bus depots to provide spare parts, even better parts for customers going forward. Yeah, with that, I thank you. I think I ran out of time. Thank you very much.
Thank you very much, Ben. Please stay on for the panel discussion. All right. Yes, you can just pass it to me. So, of course, everybody, we will be proceeding on with the next panel discussion. And this time, they will be tackling the topic, transforming supply chains with additive manufacturing, building resilient, scalable, and glocalized production ecosystems. Our moderator is none other than Dr. Terry Wallace, Distinguished Fellow of Advanced Manufacturing, Wallace Associate, powered by ASTM International. And our panelists, they are Mr. Nicholas Moulay, Director of Additive Manufacturing, Boeing, Mr. Sri Shetty, Chief Executive Officer, OIC International, Mr. Jim Golden, Vice President of Sales and Marketing, Fabricate Labs, and of course, Mr. Benjamin Moy, Vice President of New Ventures, ST Engineering. Let's welcome all of them, please.
We are back. Gentlemen, thank you for taking time from your busy schedules to give your presentations. They were excellent. And now a chance to have a little bit more dialogue, some Q&A, and maybe a little bit from the audience as well. So let's get started. So it's really focused on transforming supply chains with additive manufacturing, building resilient, scalable, and glocalized production ecosystems. So I've asked our speakers to submit questions to me over the last couple of weeks, and they did. And they were very good. And so I grouped them into 4 categories, and I've chose to ask many of those questions back to them. The 4 categories are the adoption of AM for production applications, distributed and on-demand manufacturing, reshaping of supply chains, and then finally, this region of the world. What's specific to Singapore and the surrounding area that makes you special? And so with that, I'm going to ask the first question around the adoption of AM for production applications to Nick. Okay. So Nick, how would you characterize the current state, and this is not just aerospace, because I know you attend a lot of events around the world, you've been around for a very long time. How would you characterize the current state of AM for production applications?
Yeah, thanks, Terry. Maybe building on what I was talking about at my presentation, I think we're there. We're doing production and additive today. I think if you're looking across certain industries, we heard early this morning in opening remarks, some are in the thousands or even millions of parts. And the fact that in aerospace, we're getting in thousands of metal critical parts tells me that, we're really there in production today. And so I do want to emphasize it's kind of the inflection point is, I've been in additive for 10, 15 years on metals, a little bit longer for other processes. And there was a lot of that focus on, a company might have the 1 or 2 applications to really justify the investment. But now I think we're there from a technology standpoint. And I think now we're at the point to scale additive comes down to a lot of the infrastructure and some of the other topics we'll probably talk about today, and also just continuing with some of the customer buy-in in certain industries where we still have to overcome some cultural hurdles, some regulatory hurdles when it comes to willingness to adopt it. But I would say I think we're there, honestly, and I think it's a exciting time now to figure out how do you take the next level in quantity of production and just continue to have an uptick in the percentage of manufacturing. It's still relatively small, but I think it's getting more meaningful.
Would you agree or disagree that cost is still the major obstacle to broader adoption?
Yeah, I think so. I mean, I think that is still, from the accounting cost, the unit cost, for certain industries, that's a clear line in the sand, and trying to figure out how do we reduce that cost overall. But I think in certain industries where there is the opportunity cost of not doing it, or looking at the economic cost, if you're looking at saving time in some industries, trying to really figure out how to calculate that can be challenging. But going back to aerospace, aircraft on the ground, if you actually accumulate all that cost, it's quite significant. And so I guess what's your basis of comparison? But unit cost in a commercial market is going to be a big driver.
Yeah, okay, good. Benjamin, so what are the key drivers for a commercially viable AM ecosystem? I know it's kind of a broad question, but you wrote it, so.
I think it's the talent and competence to actually design advanced components. I think that the value add to really help the ecosystem build capability and capacity is really to have that niche space that you have. We want to talk about value as opposed to cost, because the innovative design will leapfrog what we can do today. And I think the biggest hurdle that I see in companies today is really the procurement. They come to you and say, China can produce it for 50 cents. Why do you want to produce an additive manufacturer for $3 per part? And my argument is, what's the true life cost? How long can this part last before failure? Does it live 3 times as long? Does it give better performance? versus a lower quality, lower old technology design. So I think the understanding, the readiness of the industry to build, readiness of the ecosystem to take on these more commercial deals, I think is quite critical.
Yeah. So Benjamin, you mentioned cost. Shri, I'm going to direct it to you. So how do you see the cost dynamics evolving as AM matures over time?
Yeah, so from a medical standpoint, I think AM is perfect for medical devices purely because medical devices that go in the human body are relatively small. They also are complex and done in complex materials like titanium, cobalt, chrome, where historically traditional manufacturing has had a lot of issues with developing high quality parts. So AM is good in an industry like medical. If you look at the history of AM adoption in orthopedics, it's pretty phenomenal in the US. Orthopedics is a $70 billion industry. 0% of orthopedics was 3D printed in 2010. Today, if you look across the orthopedic industry, almost 98% of spinal cages are 3D printed. A lot of trauma is 3D printed. A lot of knees are 3D printed. So it went from a $0 industry 10, 15 years ago to being a pretty significant $10 billion, $20 billion industry today. The challenge is, though it has seen significant adoption in the US, the rest of the world is still using traditional manufacturing. And the reason is that the cost pressures in the US are much lower than the rest of the world. If AM has to be adopted to grow through the world, it is very critical that along with the advanced technologies, there are other advanced models like joint ventures, government support, local factories, digital factories, added along with AM so you can put the factory in country to bring the costs down. Because in terms of performance, it's a no-brainer. AM will dominate medical. The challenge is, in order to bring this high performance, high quality devices to the rest of the world, you need alternate manufacturing models and you need alternate business models. Otherwise, it's a challenge. The cost is very critical for the rest of the world compared to the US, especially in medical.
Yeah, for sure. Yeah, speaking of the popularity, the growth of AM for orthopedic part manufacturing, Stryker, a manager there, once said to me that 100% of their product will someday be manufactured by AM, which is, when you think about that, staggering.
So Stryker, started in 2010 with 10 printers. They have 200 plus printers in Cork Island.
Yeah.
You think about Medtronic, J&J, they partnered with Jabil. They have seas of printers out there. Orthopedics is a great space just because it gives you such a high performance benefit and people are willing to pay for health. Yeah. It's a great industry for AM. It is very Western focused because along with the performance, you require a cost structure around it, which is where we are trying to disrupt that model. Yeah. Performance by itself is not enough in the Eastern countries. So that's where you need alternate models to bring the cost down.
Yeah, most of the parts you see from those, not only Stryker, but also their competitors, are the trabecular surfaces, and which offers a better osseointegration of bone.
It is, the way different companies explain it is, the human body is bone. Bone is 90% air. When you get something out of a traditional manufactured tool, it's predominantly 99% metal. What happens with 3D printing is you can make parts that feel, look, have surface structures like human bone. So when you put a 3D printed implant in the body gets fooled to think that it's another piece of bone, so growth is faster. That's why orthopedics, bones-like structures titanium is a great segment for 3D printing. And it's pretty much, unlike other industries, the adoption in that sector has been exponential in the last 10 years.
Jim, I'm coming to you after. I have one more for Shri, so forgive me. What are the economic trade-offs of scaling AM compared to traditional manufacturing? The economic trade-offs, yeah.
So there are pros and cons of both.
Yeah.
The the big challenge with AM today is the fixed cost upfront. The machines, the printers are very expensive compared to a CNC tool. So when you actually, as you know, other industries start adopting these machines and more machines are sold in the market, it is just, you know, a matter of scale that the cost of these machines, the price of the machines will come down. But till then, the fixed cost of the machines are a big issue. That's why government support in developing countries for machine buys is very critical, because you can never get to the cost structure without it. The place where AM is great from a cost structure standpoint is labor development. If you look at a CNC tool, you require one CNC technician per tool. Training and scaling that up is very difficult. While with 3D printers, you can put 5 3D printers next to each other and have a couple of technicians work. The people scaling is not an issue. It is the fixed cost, printer cost that is the right up front, which is the other challenge is machines getting obsolete. As it's a new technology compared to CNC, every few years these machines have new features that make you obsolete. So you know, you have to be very careful of how you put down the fixed cost. But once you're able to deal with the fixed cost, either through government partnerships or joints or grants, the operational costs are much lower in 3D printing compared to traditional manufacturing, because the labor part of it is not there.
Right.
The training part is a lot easier. You know, the scaling part is much easier because it's a digital scale versus a physical scale. So,
Yeah, agree.
Can I do a quick ad?
Yeah, of course, please.
Yeah, I think I always think when you think economies of scale with a large plant and you see the traditional curve, I think additive is very predictable. Print time times number of machines, you got that linear relationship, so it is capital intensive, fully agree with you. So I think the one counteracting force is the economies of scope. So the economies of scope, I just want to really highlight that, because now you've got a fixed tool or a fixed machine, expensive, and you have to overcome those hurdles.
Yeah.
But now with the right design know-how and the additive expertise, you can use that in an infinite number of ways.
Yeah.
And so if you can use it from that perspective, it helps you broaden a broader portfolio of products that don't require unique investment for each one. And so that's kind of you have to balance that.
Yeah, no, good point, Nick. Before we switch to our next topic, Jim or Benjamin, do you have any comments on the adoption of AM for production applications, either one of you?
You know, I'll say that it somewhat depends on the industry and the application, and there is a lot about the opportunity cost. So in the case of high volume production, cost is going to be sometimes king, right? If you're making thousands of units a month, cost is going to be extremely important to an end user, a customer, right? However, if you have a situation where, let's say you are running a piece of construction equipment, it's big diesel equipment, you don't know, it could be 10 years, 15, 20 years old even, and that piece of equipment goes down. Now, traditionally, you may have said, you know, the replacement parts could be very low cost, maybe $10, maybe $50. That's great, but if you can't get those parts for 3 or 4 weeks and that piece of equipment is lying dormant and you've got a construction site that's held up until you get that part, would you pay $100 for that part? Would you pay $200 for that part? It changes the equation. And so when you think about production of AM, keying in on what you just said, Nicholas, is that, you know, you've got that economies of scope. So now you can produce 1, 2, 3 of something. You don't have to make a large run on some fixed equipment and then store something in inventory. So it does offer that up as a business model now in a way that you couldn't do before with traditional manufacturing.
Great, thank you.
Yeah, agree with Jim. I think that the whole economies of scope, I think that's a very nice phrase to use. I think that encompasses quite a lot of the mindset change. I think at the same time, there's also a need for top-down mindset push, that there is a hard decision that we are going down this path. And that was the hard decision that back in the day, Siemens Energy made to do the transition. Today, they carry 80 over 3D printers in-house to do manufacturing. And that's something that needs to stem from the top and overcome that hurdle before adoption really takes place. Yeah.
And maybe we're bringing about cost. For me, I think about cost when it was made traditionally one way. How does additive compare? But I think when I'm looking at a product only exists because of additive, I talked about earlier, like it exists because additive technology.
Yeah.
And that product has a performance or something that wasn't around before that's really enabling. Cost is important, clearly, but that linkage, it's just not possible without it.
Right.
It's just a different mindset. Yep. It's the value add versus looking backwards on how does a unit cost compare. It might have a niche for certain areas, but it's really focusing on the AM-only designs open the door for things that really solve other needs.
Right, and the opportunity to create brand new streams of business.
Yeah.
Revenue streams, yeah. Okay, let's shift to distributed and on-demand manufacturing. So Jim, this has to do with procurement. What procurement model best fits on-demand AM in terms of per part pricing, capacity subscriptions, and manufacturing as a service?
So that all depends a lot on the use case and the individual scenario. So I've seen several that are, obviously economies of scope are great. So if you've got additive equipment, you can have very high mix and relatively low volume. It's all about equipment utilization more than anything else. However, if you've got a production schedule and you're offering like Fabricate Labs, we're a service bureau, and someone calls us and says, hey, I want one part. It might be difficult for us to incorporate that one part into a production schedule. The equipment's already booked, right? So I've seen models where you can either, as a customer, you can buy capacity, like this equipment is mine, I'm going to use it. I'm buying capacity in your facility so I can use it any way I want. Another way that I've seen it work is in the case of sand casting. So you can make molds in sand and ship them off to a foundry and just pay by the pour. I've seen other models where you can pay by the kilogram. So I'm going to buy capacity, but it's going to be based on the kilograms of material that I use. Up to a certain amount, it's going to be X dollars a kilogram. Above that and to the next tier, it's going to be Y dollars per kilogram. And so that can work as well. So it all depends on whether it's a one-off part that you need to have made, or is it more of a high mix, lower volume, or is it high volume? And that's really going to help define what the model needs to be.
Yeah. Were you going to say something, Sri?
Yeah, I think this is a topic very close to my heart. We as a company have 100 plus hospitals globally that we supply devices to. Every hospital, we keep inventory at the hospital. And we think about cost of manufacturing, we think about cost of additive, we think about cost of production. But in the last couple of years, the biggest challenge for us has been the cost of moving parts from factories to different countries. It's the shipping cost, it's the time things are getting stuck in customs, it's tariffs. It is this, we've gone from this central model with shipping routes, supplying parts across the globe, and that is breaking down. It's taking us, the more time it takes you to get parts from a factory to a hospital, the more inventory you have to hold out there because that increases your cost. So your fixed cost keeps on going up. And that is where I think this model of having local manufacturing in country, because 10 years ago, the cost of manufacturing was maybe 80% of the cost of the product, and 20% was supply chain logistics. But with tariffs, shipping, customs, 90% of US customs doesn't even know how to deal with the tariffs anymore, so it just gets stuck in the port. The logistical costs are becoming almost half the cost of your product. Wow. At which point, between inflation and logistical costs, manufacturing in country becomes the only way for you to have a cost benefit over, like a distributed supply chain or a distributed manufacturing chain is the only way for you to get over these, because the current supply routes can't support it anymore.
Interesting and sad. Yeah.
I'll add to that because, if you think about high volume manufacturing and you've got to ship over a long distance, the longer it takes for you to get from the point of production to the point of use, the more inventory you need to ship at the same time. So you have a shipping cost and a carrying cost for that inventory. And you know, if you're talking very small parts, that might be somewhat negligible. But if you're talking very large metal components, very heavy components, then those costs explode, really. And so then you've got them waiting, you've got this inventory at a customer site, so they're waiting for a shipment, they get a large shipment of components, and they slowly burn that down, and then they get another shipment. So that inventory is sitting somewhere in a warehouse. That inventory can be damaged, it can be lost, or it could become obsolete because of a design change. So there's a lot of other costs that can impact that inventory beyond even what you paid for it. So to your point, if you can make production closer to the point of use, you can eliminate all of that.
And to add to that, you know, countries like China, et cetera, have spent 20 years in putting together large casting houses across the country. For any country to do local manufacturing, I don't even think there is enough space in the country to put casting houses in there. So the only way for you to do local manufacturing is to go with technology and try and use digital technologies like 3D printing to do it in country. That is what has been all my discussions in the last couple of years with the government of Indonesia or the government of India, because otherwise there is no way for you to do local manufacturing, and the supply chain issues or the distribution issues are going to continue to be a big problem for mass supply, specifically for medical and other critical care functions.
Yeah, interesting.
Yeah, maybe I'll add definitely if you have local demand, being able to produce it, you know, at the point of need, all the travel logistics that Jim was talking about, that, I mean, that solves a lot of problems.
Yep.
I think the thing that really comes into my mind is now counter that with complex manufacturing process. You know, forget the size and scale of this, like a casting house or a foundry. Those are huge and obviously not something you can just set up anywhere. But there's a lot of expertise to do high quality product there. So I think the distributed model is key to have accessibility, but I think you have to have control variability, make it repeatable. How do you scale that? Not, you know, that's kind of what I was speaking about earlier. Is additive is great opportunity. You have a little foundry in a box. If you now have you lock down all the key controls. You know, you have your machine instructions that have already been proven out. You've got a qualified powder. You've got a qualified machine. You're starting to put a little bit more control around the key inputs. So now that with just validation that things are in fact the same as another site, then you can start scaling the model kind of like a hub and spoke. But the connection on the spoke model will be based on how well you can control it. So I think the model is really needed and solves a lot of problems as long as you're set up to replicate it truly.
So Nick, in your presentation, you mentioned that you have AM facilities at 20 different sites around the world. Is that right?
Of different types and printers.
Different types, yeah. Are you doing actual production parts at most of those sites?
Not all of them.
No?
So I think you know, there's key sites for production, and kind of when I'm looking at scaling, you know, within that model, it's either key partners or new Boeing sites, being able to do that more efficiently. Because I think we know how to do it now. You set up a new site, you have to do a lot of development. Can we be more efficient and more controlled to validate it? So that's kind of where we think we need to go as an industry, and I think additive lends itself nicely to that model.
Yeah, for sure.
Yeah, I actually have a question for you, Nicholas, on that. So if you've got, and I'm sorry, Terry, but this
No,
is
that's
something
fine.
that just struck me here, that, you know, if you've got the same printer in multiple locations, and technically you could make the same part in any one of those printers, obviously on any one printer, you're going to check for repeatability. Can you make the same part over and over again, and it's the same dimensional characteristics, the same performance? Do you also periodically then need to do reproducibility across all the other printers in the field? Like you've made this gold standard part, and you make it in each one of those other printers, and you make sure that they're all producing that same part. Do you have to do that on a regular basis?
There's a lot of checks and balances. Think the initial develop a supplier, develop a machine. Like in aerospace, you're actually qualifying at the serial number level, and it's pretty involved. And so you're doing a lot of those up front. Machines configure the same. You do enough prints and characterization. Okay, it's behaving the same. And then within a company's quality management system, you're going to have build level checks. You're going to have periodic maintenance. So there's a lot of different aspects where it's not just one thing, but you're doing all those things throughout the life cycle, continuously getting data. to prove that out. Because really the key is the machine's behaving the same and it's continuing to behave the same. And you can do that in a handful of ways through witness coupons, through data analysis, which comes in the digital thread. You're able to pull in fleet data and say, is everything looking okay, data source-wise, and then through physical testing. And so I think in aerospace, you have to have several checks and balances to do that well in general, and then emphasizes it as you're scaling it.
Yeah, we have the same thing in medical. We have 14 test spots on every build that goes through. It's an added cost, but it is, while there is variability in the printers, it's a testing on the part is the only way for us to confirm that it matches part to part, printer to printer.
I think aerospace has an additional baggage of doing the POA and DOA per line. And if you want to do that across all sites, that's going to be quite costly. So I think in my mind, even back in the day, we have dedicated lines for dedicated components, and we don't shift too much from that.
Oh, it's same in medical. My first printer I bought for $650,000. It took me almost a couple of $1 million to qualify it with the FDA. The IQ, OQ, PQ, and every printer we go through an IQ, OQ, PQ, which is a 6-month process. And it does go down as you buy more printers and you get more data to look at it, but it's an expensive cost. It's a bigger cost than the printer is the qualification of the printers. And that's the bad news of doing regulated industries, that you're stuck with all this qualification and testing cost.
And then it's locked down too. You can't upgrade the software or make any changes to the machine, right? For the most part?
In today, yeah, and that's in the future that you have to figure out how to be flexible to take advantage of new technology. That's the paradox, I think, as AM leaders is we know what's needed today, but you want to keep investing in how could you do it in the future, but that takes a while to develop.
Yeah. So Benjamin, so this is a bit of a broad question, but I think it's interesting. So what role does digital inventory and on-demand manufacturing play in the future of supply chain? So if you look in your crystal ball and look out there, what are you seeing there?
Yeah, I think that's the only way to go. The manufacturing plant, production plants these days, they've done all the cost out. You can go to robots and all that, but holding inventory is quite a heavy burden on the warehouse. And be able to have distributed suppliers around holding inventory is not sensible. So we come to a point that digital inventory will be the only way to go to do cost out, and the only way to have the ability to distribute and manufacture parts on site at location. I think that is the only way industry has to go today, or in the near future at least.
So I know it's not going to be like flipping a switch. It's going to be a journey, a transition over time. Take a company like John Deere, where they have inventories of millions of parts on shelves, and if you have a tractor from 1945 and a part breaks, they will get you that part. It may take a while, but they'll get it to you. They may not have the tooling on the shelf. They may have to do some searching, but they will get the part to you. They would like to transition to that digital and on-demand manufacturing model. What's it going to take for a company like that? Or maybe it's just a 30-year program. I don't know.
Hopefully not too long. I think when we move from pieces of paper recording schedules to the Excel, the whole data transition took a lot of time. So we converted the 2D drawings to 3D drawings that digitalized. That took a huge amount of data entry and manual labor. And it helped that parts get obsoleted, so you can work on the new stuff with already digitalized. I think that's a process we need to do. I think taking the John Deere example, a lot of this inventory ends up not being used and they rust. There's a waste of material. You still need to dispose of the waste, and there's a loss of income, revenue. So the cost out portion, it weighs more on the pros to go digital today. You have the benefit of selling a license to another manufacturer to produce the part, and they pay you for royalty as a long tail theory, if you will. You get extra revenue for doing nothing. Just possibly the liability behind it, maybe. But going digital is the way to go. I don't want to carry 2 boxes. I want to carry a thumb drive, and I go to my machine, my vending machine, I plug it in and I press print. That's where I want to go.
Yeah, adding to that, I think of it 2 ways. One, if you snap a line, I have a product that had AM from day one. You already have the build files. It was part of your production system. It's technically on a digital shelf. And in the future, when you have to replace it, then you invoke this model we just talked about. That's very clean and it's ready. I think the challenge is going back to like the John Deere example or the spare and repair example I gave. Whichever, depending on part complexity or industry, it requires investment to convert it. Maybe it's a day or two if it's a simple part and a non-controlled industry, but it takes time and energy to get it ready to be printable and say it works. Then it can be put on a shelf. But the development time, you might have a very complex flight part where you have to do a full redesign, redevelopment, qualification. If that takes months or even years, I think it just keeping in mind that investment needs to be done to have that digital file ready to go. That qualified build file has a lot of weight to it. But if you build that inventory up over time, then you can pull from the shelf, but you have to decide as a company or as a strategy how to do that.
How to do it,
It's a financial...
Selective. And I guess today there are digital tools that are able to do the conversion 2D to 3D using AI today. Getting better, not there yet, but I think that will help speed up the process.
But if you look at a lot of sectors, right, the new part market compared to the repair segment, like oil and gas, for example, if you speak to ADNOC or Aramco, the repair segment is so much bigger than anything with the new part, because there are very few new pipelines going down. There are very few new turbines going down. But they have all these lines that require parts every day to be repaired. And that is where there is a huge value with additive as well, because getting parts shipped to get repaired, to come back, it could take weeks. And with oil and high commodity items, that repair segment is the other place where localization of manufacturing becomes critical.
Yeah, good point. All right, so let's shift to reshaping of supply chains. So, Shri, how is AM reshaping traditional supply chain models?
As you said, the AM is very critical in terms of localization, like I said. So, reshaping historically the models have been, you buy a part from a faraway country and you get the part shipped to you. While with AM, the model is more like we have a part, we use it as we go, and we have less stock on inventory on the shelf. And that is the biggest value. I think that the place where AM helps the most is time. From when a part is built to when you get it, from point of build to point of use. And the shorter you can make that, the less inventory you need, the less cost you have, the more mass production you can go into. I think 20 years ago, the current supply chain ecosystem worked, but as we start growing in terms of population, in terms of consumption, a distributed model is the only way to do it. And AM, it will be critical. Unlike most people realize, all AM parts do require traditional manufacturing as well. So it's a combination of AM and traditional, more closer to the point of use.
What I've seen so far is the big change that we have in our production. It becomes modularized. We don't see product lines. We see combinations of, and based on demand, we can do a portion of product A plus product B, product C, and we can switch the mix tomorrow using the same fleet of 3D printers. And if the design methodology, the design concept is correct, that will work. And it is starting to work within ST today. We're able to do multiple nestings of different parts for one module, one component, one product line, if you will. And that sort of changes the concept of production lines for products. It becomes a mix, metrics of production capability.
Yeah. So Jim, global manufacturing, that's an interesting term. I'm warming up to it. What does global manufacturing deployment look like? I mean, if you were explain it to people who have never really heard of the concept before. In your view, what does it look like?
So it can take a couple of different forms, I think. I think global, which I'm not quite as warmed up to that particular term, but it's global and local. right?
Right.
So it is a distributed manufacturing methodology. So you may have a centralized design that is then manufactured in multiple areas, regions, factories around the world, right? So what can that look like? That can look like, you know, you may want to put a factory in Singapore and another one in Europe and another one in North America, and that can be your kind of global manufacturing. However, there are other things you can do, particularly in the world of additive, because you know you can do a lot of part consolidation with additive. You may be able to get away with using much less floor space, and so you can actually put your equipment inside of a customer's facility so that you can produce parts on demand for them to use on their own production line. That can take the form of either them buying a printer and running it, or they could be leasing equipment from you so that, you know, you're getting a license fee from them to run your equipment. Or you can even set up a factory within a factory. And this is something that I'm seeing, you know, a little bit more of in some of the areas that I'm in, where you can license the technology in a way, but you're also bringing your own people to not only run the equipment in the factory, but also to provide some assistance with the design for additive manufacturing as well, which is one of the key barriers to adoption of, I think, additive manufacturing in production, is the ability to design parts for additive, right? Quite often I've seen designs come from engineering that would obviously be easier made just CNC machining, you know, or are so complex they require to be cast, but they just want to make it an additive, and that's not necessarily effective. So having that capability in-house is extremely important. But so how do you develop that capability? Many times, if you can go to a provider and they are actually operating the equipment in the facility, you have access to that knowledge that they have accumulated by working with multiple customers in different industries even. So they can bring that knowledge to bear to help educate you in how to use additive manufacturing. So those are kind of the basic models. So you can either, you know, have a factory in a factory, you can lease the equipment, or you can just have like factories set up in different regions that can support a large number of customers in an area.
Good. So, Benjamin, you live here in Singapore, right?
Yes, yep.
Yeah, okay. So, with increasing adoption of AM in Europe and the US, why hasn't it taken off in Southeast Asia?
I think that's a very good question. I think it's also a bit of control, I guess. A lot of the manufacturing design comes from the HQ, US, UK, and Asia in general is a manufacturing house. We take designs, we produce quantity and quality meeting your specs. So I think there's a big gap in understanding that at least the Singapore ecosystem is ready to do this advanced manufacturing. We have a lot of research institutes that have done tons of work on new material development. We've done a lot of fan blades for the aerospace. We've done MRO printing, 3D printing. So we have that capability. I think the element is the quality is there. Can we trust it? Do we need to get additional certification? Do we need to deploy some of the issue guys come and work with us to show that we are ready? So I think the AM in Singapore has been growing in terms of capability. We want to showcase not just a simple impeller replacement. Yeah, we can't compete with China in terms of costs. We want to do things that are even more exotic, more complex. And I think that's the element of trust that we need to build and confidence we need to build with Europe and US in order to be positioned here, that we can do some of the loading for 3D printing. So some of your portable build files can be sent over to Singapore, and we do the same file, and you do the QC as well.
Yeah, so to expand on that thinking, you know, how can Singapore in particular become more commercially viable? And it's for questions for you and the rest of the panelists as well, if you have ideas.
So I think for us, we're globally positioned in all these places. And by having that capability be positioned closer to the R&D guys in the US, for example, to build that confidence and say, we are the same company, we are able to bring the MRO capability and share with our local teams here, and across the different aerospace MRO sites that we have around the world to support Boeing or other aircrafts in that light. Yeah.
Jim, Shri, do you guys have operations here in Singapore?
Yeah, we are just about to open up a training development center here in Singapore. But going back to the comments. I think one of the key thing is AM as a technology truly came out of Europe and parts of the US. If you look at the university ecosystem, a lot of universities in the US actually got 3D printers some time ago. So there are some programs in some of the different universities that actually teach AM as a technology. Anyone that has used a metal printer will realize it's not the easiest thing to use in the world. It has its own quirks, and it's more like black magic, putting in a file and getting a part at the end that meets all the requirements. And it's held by a few companies, and it's held by a few individuals, and it's held in few parts of the world. I think Germany has high quality. I think Ohio has high quality, and a lot of the core tech is held there. I think if we need it to be a more mainstream technology, we need some of the more, we need the technology to be easier and more user-friendly, and we need more people educated in using the technology to build parts, which is lacking in the developing countries. Finding engineers a lot of our engineers, we have to ship them back to the US to train in Ohio and come back. There isn't any local program to train people to do it. While in CNC and other technologies, there are a lot of tech programs around that teach people how to do CNC or how to do machining, which does not exist in AM today in the developing countries.
Nick, Jim, do you have any comments, any suggestions for what Singapore can do to accelerate its position in AM globally?
No, I mean, I think they're good comments just on additive being complex, and when did you first start? And if the machine was developed in a country, the time to understand it and build up supply chain, that's just inherent. So I think it's more, I think, even in the United States, trying to scale additive still has challenges. It's a universal thing we have to figure out. Maybe
It really is, yeah.
So if it's universal, then it's how do you lower the technology barriers, which is taking a controlled process and reducing it down to practice to scale in production, which can be in any region.
Right.
And then the region that has the workforce or the local needs, that's going to apply pretty much everywhere. So, I think it's, taking 10, 15 years ago, the PhD metallurgists, and to scale it, you need to reduce it to a scalable manufacturing process. So I think it's a universal need, frankly, and it's, learning more about the region is just something on my mind, which is just helpful for me to learn.
Yeah.
That's why for us it was very critical to put a training center in Singapore with a printer that our workforce could come in from Indonesia, from India, get hands-on training on it, because it's not very intuitive on how to do some of these technologies out here. So I think training infrastructure is very critical.
Yeah.
And maybe I'll just add, listening, and a lot of the core R&D work through NAMIC and A-STAR, building up that foundational knowledge, that's key. And any adopting, region has that fundamental expertise to really understand the details to then help develop supply chains. So I think that's an example. It's just important, is there's a lot of complexity to have to understand.
So the universities here in Singapore, I think, are doing an outstanding job. Are the graduates finding work in additive manufacturing here in Singapore, Benjamin?
I think we have the talent, but we don't have the exposure. I think that's probably the baseline. So we do a lot of simple obsolescence replacement, impellers and stuff like that. And a lot of our talents actually try to position with other more global companies, that they get pivoted back to Asia to learn more. I think that's where they find more interesting industrial projects to do. And I think that's what's lacking in the Singapore ecosystem, where we're not getting interesting parts to redesign and really stretch the talents that we have. So we've seen quite a bit of an outflow of some of our AM trained people going out more to Europe, more to US to get a little bit more niche exposure, if you will. But from a manufacturing perspective, we have operators that have worked on machines for a long time. I mean, the designs are complex. I think that's the gap that we see. We have a very solid structure and training for AM and getting the talent out. It's just the experience that's sort of lacking, industrial experiences that I feel is lacking.
Yeah. I think that's a great way to conclude this session. Our time has expired, so I'd like to thank our panelists this afternoon. Thank you very much. and enjoy the rest of your afternoon.
Thank you very much. Gentlemen, could you take a step in front of the tables for a group photograph? So, of course, everybody, in just a while, we will be adjourning to tea break. I'll need your help to be back by 3:15. And at the same time, could you just refer to the back of your lanyard? I believe there is a QR code over there. We'll need your help to fill up a survey form to let us know, if there are any areas that we've done well and if you think there's any areas of improvement that we could be looking into. Thank you very much, everybody, and we will see you back later on at about 3:15.